My previous video introduced the binomial option pricing model, but in that version, I just arbitrarily made up the values for U and D. U and D represent respectively the magnitude of the up and down jump in the model. So they inform this stock price tree here. How much does this $20 jump up or down in the binomial? Now I'd like to just articulate the intuition behind a common step that we take when we use maybe the most popular version of the binomial option pricing model. That's this version. It's called the Cox-Ross-Rubinstein. And in this version now, we have a volatility input assumption, just like we do with the Black-Scholes, and we let that volatility inform for us the U and the D, or as John Hull says it, we match volatility with U and D, so we don't need to make it up. Why does that work? What's the intuition? That's what I'd like to show you now. So my baseline assumption here is a two-step binomial option pricing model based on the same assumptions that are found in John Hull's textbook. That's the 10th edition. This is assigned to FRM candidates. And you can find that at figure 13.4. So that's in chapter 13. Although my presentation differs in terms of the stock price tree that we build out and the option value node, I'm using the lower triangle format because this is only a two-step binomial. That's unrealistic. When we get to more steps, this triangle format ends up being, I think, much more convenient. So we break out the stock prices up here and the option value nodes here. And this process is leading us to the solution, which is found right here in darker purple. The price of this 6-month option per a two-step binomial, you can see, is 95 cents. That's based on assumptions here. You can download the spreadsheet, which includes the ability to toggle this between a call or a put. Small c, I remind you, denotes European, not American style call option. We have an asset of $20. So that's S sub 0, that's the price at the time of purchase of the option. And the strike price here is $21. So this call is going to be slightly out of the money. Key input here is the time per step or per interval. As usual, our input assumptions are always in per annum. So the time step you can see here is 0.25 years, which of course is 3 months. And that refers not to the overall life or maturity of the option, but rather just the time per each step. This is a two-step binomial option pricing model, and so that's 2 steps times 3 months per step. It's 6 months to maturity on the option is this assumption. So I'm not going to use a volatility input. That's going to be in the next sheet, because here I'm just setting up the baseline to show you the difference. Our risk-free rate is 4%. I'm assuming a dividend yield of 0%. And then we have the solved for parameters that are the key ingredients in this binomial option pricing model. So in green they're solved for, and in yellow I have the 2 inputs that we manually specify, same as I did in the last video. But you'll notice the P and 1 minus P are solved for, and I mentioned in the introduction video that these are solved for that important component here of the binomial option pricing model, which is risk-neutral valuation. So the risk-neutral valuation allows us to solve for the probability of an up jump in this binomial model, which is given by E raised to the R minus Q, risk-free rate minus the dividend. That quantity is the A right there. So we didn't need to explicate the A, but sometimes this makes it a little easier to explicate the A. That's just the A right there. And we subtract D, magnitude of a down jump, divide that quantity by the difference between U and D. So P is solved for us per that formula. And why do we have that formula? Well, it's necessarily true in the risk-neutral valuation framework, where that basic ideas were allowed to solve for this in the risk-neutral world and transfer the truth of that over to the real world. So we get the probability of an up move, and therefore 1 minus P is the probability of a down move, and you can see those probabilities are respectively 55 and 45%. What I needed to provide as I did in the last video introducing, is values for up and down. And here I followed John Hull, assuming that if the stock jumps up, it'll go up 10%. If it goes down, it'll go down 10%. So we have multipliers of 1.1 and 0.9. And you'll notice there's a symmetry there in the plus 10 or minus 10%, right? So plus or minus 10%. These are manual assumptions under this baseline approach that I'm going to replace in the next sheet. But we needed the up or down, of course, to specify the stock price tree. That's that first major step in the binomial here, where we start with the initial asset price, S sub 0, right? And that in the binomial, by definition, that price at each step is going to either go up or it's going to go down, where in this triangle format, down is just, to go down is to stay on the same row. So you can see the $20 either goes up by 10% to 22, or it goes down by 10% to 18. And similarly, the 22 either goes up to 24.2 or goes down to 19.8. And I do have here, I've included in this exhibit, this worksheet, this row and column, which help with the notation. I like this tree notation. I got this from Bruce Tuckman, actually. And that is to say, this $19.80 right here, well, that is, we could refer to that as the node at date, comma, state is the way that works. So date, it refers to counting over the number of columns starting at 20. If we go 1, 2, we're 2 dates over, like that. And then we start at the bottom with the 0. So the 1620 is state 0. The 19.8 is state 1. So the $19.80 is the value at the node 2, comma 1 if we want to reference. But that 1980 is equal to the $20, the initial stock price assumption, multiplied by an up jump, multiplied by a down jump, which of course is $20 here, multiplied by 1.1, and then multiplied by 0.9, right? So we could go up and then down, and we get there. And as I mentioned in the previous video, we're keeping things simple with a recombining tree. So this $19.80, we also get to that same value if the $20 were to go down then up, if we switch them around, right? So $20 could drop to 18, but then go back up to the same $19.80. So that if we have 2 steps, we're necessarily, by definition, going to end up with 3 terminal values. And so that first major step is a simulation forward. And so the point of that is to retrieve these 3 terminal values. That's at the end of 6 months, right? 2 steps, each step is 3 months, so 6 months to maturity of the option. So really this terminal, this point in time is determined as a contractual feature or specification of the option contract. Happens to be 6 months here, it could be 1 year, it could be 3 months. So we take the terminal values and then perform the second step here, which was technically, we called that backward induction, you might recall. And in the backward induction, we're really just implying a fundamental principle of finance, which is we're computing the expected discounted value at each node. So if I take this this $1.74, which happens to be at the node 1, 1, right? Date 1 step, state 1 step up. Node 1, 1 has a value of $1.74. How did I get that? It's just expected discounted value. There's a 55% probability of a forward option value of 320 based on the intrinsic value at termination or maturity, or there's a plus a 45% probability of a 0. So 55% multiplied by $3.20 plus 45% multiplied by 0 gives us that expected value 6 months forward that we then discount at the risk-free rate. I think I covered that in a little more detail in the previous video where I introduced the binomial. Don't want to go into that right now, but just to remind that we're getting this node with expected discounted value. Same here. The expected discounted value of 2 zeros is just 0. That one's easy. And we get expected discounted value. One more step as part of the backward induction gets us to the option price of 95 cents, which by definition here then is a present value. Of course, the option pricing model is computing for us a present value. However, now, point of this video is really that we had to go find an up and down, or go make up an up or down value of, in this case, plus or minus 10%. And if that feels arbitrary, I think it's safe to say that it is arbitrary. Why not 20%? Why not 15%? Well, that's the point of matching the volatility to the up and down parameters. And I'll also note that you'll notice this is symmetric. As we increase the number of steps in the binomial, we are also implicitly assuming that these arithmetic returns are normally distributed. I'd like to keep that in mind. This assumption here implicitly is that arithmetic returns are normally distributed. But now what I do on the next sheet, also in the downloadable worksheet if you want to take a closer look, is now I'm going to use the volatility parameter. So this is what Hall calls matching volatility with the up or down. And if I happen to use I'm going to just change that to 30%. Let's say I input a 30%. The idea here is that now I don't manually need to make up or arbitrarily my up or down inputs. And from an exam perspective, most of the time you'll be given the volatility and you solve for the U and D. So that's how that works. Now, these aren't yellow anymore. They are solved for. And the solution is super simple. The up jump is simply e raised 2, and all we have in the exponent is the periodic volatility. It's that simple. We're taking an exponential of the periodic volatility, and the periodic volatility is the 30% that we're given, right? So I'm just going to say 0.3, or here I'm just going to represent it symbolically. The up is e raised 2. Our volatility, which is in this case is 30%. However, the 30% again is a per annum, and each of these steps are only 3 months. So we scale that to the correct periodic volatility, which is to say, what is the 3-month volatility? Well, it's the 30% multiplied by the square root of time. So for FRM candidates, that should be familiar because we're employing the square root rule. What we have in the exponent here is simply the 3-month volatility that is just translating the assumption that we're given. That square root rule, of course, assumes IID. I'll put that up just up here. The independent and identically distributed, that's the implicit assumption in that square root rule, so we are using that. That's the U, it's that simple. D is just 1 divided by U. Or if we want to really explicate it, it's in the exponent we just have the negative of volatility scaled by the square root of time, right? Standard deviation scales with coordinate time because variance scales with time. But it's easier just to say 1 divided by U. So the U and the D match the volatility, or we take the volatility input assumption to infer for us what the correct U and D are. And now, why does that work? Well, John Hall actually shows the derivation of that, but I just want to show you the intuition. And the intuition is simply that we are solving for the U and the D that gives us a binomial random variable with this volatility. It's that straightforward. I'm really just restating the fundamental assumption in the first place. We want to match up and down to the volatility. Why do these values work? They work because these are the up and down values that give us the standard deviation of a binomial variable equal to approximately 30%. It's easy to forget, Well, maybe not. We have a binomial tree, and what that means is we really have at each node here a binomial random variable. So all I've done here is just transfer these over. The 1.16 and 0.861 that are solved for, if I just subtract 1, these are returns, right? Now in these revised values, the u of 1.162 is a multiplier, so it's telling us that if we jump up, we're jumping up by 16.2%. And then here's the probability P, 49.6. And here is the 1 minus the probability, 50.4. So here I'm just restating the same values, but now we have return and probability. And then the key insight is simply just to remember that this is a binomial variable. I sometimes like to think it's a Bernoulli variable because it's just up or down, but technically a Bernoulli requires values of 1 and 0. And we actually have an up return and a down return, so these are not 1 and 0. So to me it's sort of like a Bernoulli, but it's the simplest possible binomial. And what is the variance of a random variable? Well, our most important or our most common or useful variance formula, if I want to take the variance, that's sigma squared of a random variable r, our most useful property of variance is that it's the expected value of r squared minus the expected value of r quantity squared. Right, I hope that's familiar, and you could put an x in there. It might make it a little more familiar if we use an x. But that is a key and fundamental property of the variance. So all that I've done here is apply that formula for the variance of a binomial and to get it right here. So what I have here, the expected value of r squared, you can see is simply if I take the return and square it and multiply by the probability. But let me do that again. Return and square it multiplied by the probability. And you can see if I do that for the down, and then if I sum those, I get 0.023. So that's the expected r squared. And then here, this is even more simple. Here I just have the return times the probability, so that if I sum those, I get the expected return, and then I'm going to square that quantity. So you can see here 0.023 is my the expectation of return squared, and 0.00010 is the expected return as a quantity squared. So that if I take the difference of those, I am simply computing the variance of this binomial random variable. And this variance is 0.0227, such that if I take the square root of it, I get the standard deviation or the periodic volatility, which is 15.1%. And if I compare that to my input assumption, I just take the 30%, and again, that's per annum, so I want to scale that to the periodic or 3-month volatility by multiplying by the square root of 0.25, so that my input assumption, my 30% per annum input assumption is the same as a 3-month input assumption of 15% volatility. So I'm comparing it to the assumption that I was given, and you can see that's the point. Matching the volatility with the up or down, to do that is to find the up or down values that, when used in the binomial random variable, which each of these nodes is dynamically modeling, we get a variance and therefore a standard deviation and therefore a volatility equal to the volatility input assumption. In this case, it's about 15. And you'll notice it's not exactly the same, but if I put this down to 20%, I think where I first found it, you can see they're gonna again approximate each other, but it's not gonna be exact. And if I take that out, and that's because Hall in the derivation, this is a mathematical derivation to make these match. However, to keep the derivation simple, he is allowed to ignore some higher power terms in the interim math that they just shave a little off the difference. So we end up with a little bit of an approximation. So I think it's fair to say this will always be just slightly different than the actual input value. But we now don't need to arbitrarily guess what the up or down is. We're using the volatility input assumption to inform it. And the final thing I would just say about that is that recall in my baseline where we used arithmetic, we were symmetrical with a plus up, plus down. I said that implicitly, that's arithmetic returns normally distributed. Here we're not symmetrical, right? That's because down is not equal to negative up or 1 minus up. It's 1 divided by u. It's the reciprocal of the up. So these aren't symmetrical, and you can see that even visually here. This is 10.5% jump up, but it's a slightly less than 10% jump down. And so if we scale this out with multiple steps, implicitly what we have here are geometric returns, that is to say, continuously compounded returns. We're assuming those are normally distributed, and I'll just denote that like this, approximately normal. When we do this, we're assuming geometric returns are approximately normal, and that means that the prices are approximately log normal. If that sounds familiar, it's maybe because that is an assumption in the Black-Scholes-Merton. That's no accident. When I do this matching, or when we do this matching with volatility with the UND, we are using probably the most common use of the binomial option pricing model. It's called the Cox-Ross-Rubinstein. I'll just abbreviate that CRR. And that means, because we are assuming that geometric returns are normally distributed and therefore the asset price, is log normal, as we increase the number of steps, we will necessarily be converging on the classic Black-Scholes-Merton. So, binomial model itself, infinitely flexible. You can think of it as a tool set. I can put these pieces together any way I want, build out the tree, backward induce, various ways. But if I do it this way, and I increase the number of steps, then I get a value that starts to converge on the price I would get if I use the Black-Scholes-Merton. And that's because in a core way here, this linkage, this underlying assumption about the returns behavior is similar, and as the number of steps increase, it becomes virtually identical. So this is the version of the Black-Scholes-Merton. This is the version of the binomial that starts to mirror the Black-Scholes-Merton. So long video. I hope that's helpful. If it was, subscribe to the channel and we'll keep you updated. Thank you.